The previous interaction session, it was got to my notice that students are finding it a little bit difficult to relate with the density matrix in the form of an operator. So I'm going to reiterate it for a single spin half system. Once again, the easy example that we have been seeing so far, the water case, which just has only one proton. Therefore, it's just going to be having the two spin states alpha and beta. And if you might remember, the alpha state was represented in the matrix notation as 1, 0 and the beta as 0, 1. And we said the wave function is going to be denoted in the form C alpha times alpha plus C beta times beta. And we also said the mod of Ci square gives the population in state I. So this was the definition that we had been working with. And we also said that the projection operator is going to be defined as the ket psi times bra psi. So can we first write how does psi look in this representation? You're going to have something like C alpha times 1, 0 plus C beta times 0, 1. So this will be given by C alpha, C beta. This will be the representation of ket psi. So therefore, the projection operator that we are trying to write is going to be C alpha, C beta, and the bra psi is going to be a transpose and complex conjugate. So it's going to be C alpha star, C beta star. So this is going to be equal to, if you do the matrix multiplication, you start with a 2 by 1 and a 1 by 2 matrix. Therefore, you're going to end up with a 2 by 2 matrix. So let's do the matrix multiplication now. You're going to have C alpha star, C alpha C beta star, C beta C alpha star, and C beta star. Now I hope you are able to appreciate this is the alpha alpha term, this is the alpha beta term, this is the beta alpha term, and this is the beta beta term. Remind yourself of the aspect that when you have n, p, m, you're going to get Cm star Cn. So that is the same thing that you are able to see here. If you're looking at alpha, p, beta, you're getting the C beta star, C alpha. Same is the case with all the other elements that are present. The only difference between this projection operator to that of the density matrix is going to be the over bar that is present, which indicates the ensemble averaging. So now going back to the equilibrium condition that we wanted to discuss, you know that in thermal equilibrium we had seen in the case of bulk magnetization that it points along the z-axis, and you said the magnitude of the bulk magnetization is given as the difference in the population of the alpha and the beta states. And the important thing that you have to note here, we also said mod of C alpha square is the population in alpha state, while mod of beta square is the population in the beta state. So basically the magnetization is going to be given by the differences of the absolute square of the complex coefficients. So therefore, the equilibrium density matrix is just going to be mod C alpha square 0, 0, mod C beta square along the diagonal. And this already gives you an idea that the diagonal part of the density matrix gives you populations or polarization. On the other hand, the off-diagonal elements gives you the coherence that we end up generating. Okay, so now let's go back and try to understand how this can be represented in terms of the IZ operator. If you are able to correlate here, you are able to correlate P alpha to mod C alpha square, P beta to mod C beta square. I request you guys to remind yourself that P alpha by P naught, where P naught is the total population, is going to be given by e power minus alpha by kBt, which we had seen earlier. The denominator is going to be e power minus alpha kBt plus e power minus beta kBt, beta by kBt. And with the high temperature approximation, I'm sure you would remember, we ended up getting h bar omega naught by 2 kBt, the whole divided by 2. The 2 comes up because we are trying to say kBt is much greater than the energy difference between alpha and beta state. So meaning that you can go for the Taylor series expansion with only the first term being present. So therefore you end up obtaining an equation that looks like this. So therefore, you are able to relate C alpha square is going to be something as 1 over 2 multiplied by 1 minus h bar omega naught by 2 kBt. If you calmly repeat the same process for C beta square, you are going to get 1 over 2 1 plus h bar omega naught by 2 kBt. So this is what ends up going into this equilibrium density matrix, where you have 1 over 2 minus h bar omega naught by 2 kBt, 0, 0, and 1 over 2 plus h bar omega naught by 2 kBt. Now, if you pay close attention, you can take the 1 over 2 out, where you're going to have a 1, 0, 0, 1. And then at the same time, we can take the minus h bar omega naught by 2 kBt out, so that we get 1, 0, 0, minus 1. Therefore, you are able to immediately understand it's a 1 over 2 E2 by 2 minus h bar omega naught by 2 kBt times the IZ operator. So this is nothing but the, of course, I have missed one small part. That's going to be h bar by 2 will be gone. Now I had made a small mistake, so therefore the 2 would exist. This is going to be a 4, this is going to be a 4. So you're still going to have a 2 that exists, 4. So what you are able to understand here, this is nothing but E by N minus omega naught by N kBt, where omega naught the Lamer precession frequency times Iz. This is exactly how we had defined the equilibrium density matrix, where E is the identity operator, N is the total number of states, minus the Hamiltonian that is there in the equilibrium state. So if we might recollect, the Hamiltonian at equilibrium for this case is going to be omega naught times Iz. So I hope this helps you understand. For the entire density matrix, there are two terms, one that's a constant term. Irrespective of whatever you do to this term, it will not end up changing due to pulses or anything. We end up only seeing this part. And since the only part that might end up changing for all our perturbations is the operator part, we only end up taking the reduced density matrix of the form as Iz. You would be able to represent the density matrix at any given point of time in the form of the operators. Of course, identity operator is a part of it. I'm just not listing it here. And these are the coefficients. For instance, this is a coefficient that we ended up seeing for the Iz matrix in this case, which we have just taken out just so that it's a simple reduced density matrix type of an entity. Now, when you are applying pulses, you could generate a certain case where the off-diagonal elements could get populated. The Ix and the Iy matrices actually only have elements in the off diagonals, so therefore the density matrix could be represented with Ix or Iy or a combination of them based on the pulses that you end up applying. So therefore, all these four elements that are present in this matrix can be represented as a sum of any of the spin operators that you end up getting for this given set of states. So I hope once again this has helped you understand a little better how the equilibrium density matrix can be represented in this fashion, and we end up only taking the reduced density matrix represented by the Iz operator, and at any given point of time density matrix can be represented by these operators.